I think I missed the details, but I'll get them later. Maybe the most important part here. So I'm pleased to be here to talk a bit about beam management in 5G and beyond. And I do admit that my talk title evolved. I think I put data-driven in before Bhaskar, though. Maybe that was the inspiration for his data-driven as well. It's a topic that connects with MIMO, with Professor Palraj's talk, and also pre-coding, which Yorgos's group has worked on extensively. And I couldn't dig up my favorite photo, which is when I was working with Yorgos for my master's degree, we made his first web page, and we had a nice staged photo of us in having a fake group meeting for that web page. I have it in my mind. I know you've got it somewhere, but I couldn't find it. So one thing, I was doing my undergraduate degree at the University of Virginia when I met Yorgos, and I think I'll tell you all that he saved me from becoming a patent attorney. That was maybe his main contribution to me, among others, technically, of course. Now, since then, I've been working with a number of patent attorneys, and I realized I would have made a hell of a lot more money. But I think my life is better. So thank you for that. So I wanted to start off with just a little bit about MIMO communication. I was anticipating we'd hear some about MIMO, so I only have one slide here. So MIMO, I started looking at it in Professor Palraj's group when I joined as a PhD student in 1997, worked with IOSMAN that he mentioned. And so I've been working on it essentially my whole career. I keep trying to do other things, but I just always end up back to it. So I've pretty much given up at this point. I'm just going to stick with it. So MIMO has been evolving. It's a great commercial success now. It started off in these pre-802.11n Wi-Fi products. It's now widely deployed in both Wi-Fi and cellular. It's in the standards, and it's actually in the hardware that all of us have right now. One of the point I want to make here is that not only has MIMO been incorporated in commercial standards and been evolving, the numbers of antennas that are supported as well has been increasing. And you can see up to, I think this was for 5G, it might not be release 18, 17, 32 antennas at a base station, 8 at the receiver. It's actually ports, but I'll talk about that a little bit here. And we don't need neural networks to imagine that this is probably just going to continue, and release 18 and beyond is supporting more and more antennas. If 32 antennas is good, 64 is going to be better. So in the early days of MIMO, the systems like I worked on as a PhD student, some of these early experiments, the MIMO systems that we had envisioned looked something like this here. There was an antenna that had an RF chain and some mixed signal data converter, and all of the action was happening in digital. And that time it was on a really old PC that we had, and some NI NIDAC cards. But this is largely how MIMO is working in those early implementations. And so it's a realizing MIMO is a digital signal processing problem. All the signals are created in some digital form at the transmitter. They're sent over this multi-input, multi-output channel, and then they're processed in digital at the receiver here. And there's all kinds of interesting tasks. There's a lot of work that has gone into estimating the channel. You send known signals on each of those antennas to estimate that multi-input output channel. You can take that estimate of the channel, figure out how to pre-code at the transmitter, how to figure out, what are the eigenmodes of the channel. Let's try to send into those eigenmodes. So that's pre-coding, that's feedback, all topics that have been of great interest, and certainly touch on Yorgos's group's work in the wireless era. Now, one of the challenges is that as the systems keep scaling up in antennas, it becomes more difficult to get all those advantages of MIMO. And the net of it is that the channel, is changing. There's a certain coherence time. Maybe it's 10 milliseconds or 100 milliseconds, depending on the environment. And you have a certain amount of time for the users, the link to estimate the channel, to compute whatever you should do at the channel, send that back, and make use of the channel. And I'm not even accounting for supporting multiple users, scheduling the transmissions, bursty traffic, all kinds of other sundry challenges that make it difficult to make use of the channel before it changes. And these problems are aggravated when you go to more antennas because you need to send more reference signals to estimate the larger antennas. Now you can avoid this if you use TDD and reciprocity, but that hasn't been the case in most of the commercial systems here. In fact, TDD was even phased out of Wi-Fi. It was supported in 11N, and it's not there anymore in AX. So this is one of the big problems. And so as a result, if you have a lot of antennas, but you don't have enough time to measure them all, well, pretty much you just turn some of them off, right? There's not much else you can do there. So you don't get the benefits from having a lot of antennas. Second problem. So as Paul alluded to, with millimeter wave communication, it became very interesting to have large array apertures, lots of antennas. So we need those antennas anyway. I just told you it's hard to support them, but nonetheless we need them. So this hybrid architecture was proposed, and Samsung had done a lot of early work on this. I was fortunate to have a graduate student who did an internship there, and he came back telling me he'd worked on this hybrid MIMO architecture with Samsung, and it was one of those things where just like, well, he's a smart student, one of these students that was enjoying himself, so he was working about the minimum, and he's now very successful at Google. But, just one of those who's just enjoying life, going to the gym a lot. It's really annoying when you're, a tenured or even untenured professor at that point. And so he came back and he's like, yeah, we're going to put a bunch of the beamforming, we're going to solve this problem by putting it in analog. So we're going to do all the beamforming, like most of it in analog and some of it in digital. So for example, maybe you have 100 antennas and you squeeze those 100 antennas down to 10 dimensions in analog using analog attenuators, phase shifters, combiners, splitters, and then you do the rest of the beamforming in digital. Now, from a digital signal processing point of view, this sounds great. Now, if you talk to the RF circuit designer, they have a different set of issues there, because of course it's hard to really realize this. But nonetheless, the challenge here is that you're doing a compression of the dimensions. And so from a digital signal processing point of view, what the receiver now observes is the channel intertwined with those pre-coding and combining things in analog. So the difficulty here is you got to pick the analog based on the channel, but you don't know the channel to pick the analog, and then you try to measure it, everything's all combined together. So that makes it hard to do things and take advantage of all those MIMO dimensions. So the opportunity here is to leverage spatial coherence. And this has come up, I couldn't pinpoint like the earliest work on this topic, but there's a whole lot of different papers that have come out in parallel looking at this from different points of view, starting in the mid-2006s to later. But the basic idea is that while the channel is changing quickly from the point of view of the coherence time in a typical wireless textbook, and then maybe the distance is, is wavelengths or tens of wavelengths, right? So we might be talking 30 centimeters, a meter. The roughly speaking, the multipath directions aren't changing so quickly. So that car may be experiencing more or less the same multipaths over 10 meters, even though the phases of those paths as they add up, it adds and subtracts like every, 30 centimeters. And this idea, you can think about this as, we model the channel as being stationary, and the spatial correlation is locally stationary. Of course, at some point you go around the corner and things break down. So roughly speaking, the dominant eigenmodes of the channel shouldn't change so quickly as the channel realizations itself. And herein lies the opportunity to exploit what's called a beam-based approach to MIMO, or beam management. And the essential idea is to break down this pre-coding matrix that we're going to use to focus energy into the channel into two pieces. And these pieces kind of mirror what's in that hybrid architecture. There's a big frequency flat matrix, a tall matrix, that maybe takes us from 100 to 10. And it doesn't depend on frequency. It's going to vary slowly. So it's more or less dependent on that longer term coherence. And then that smaller piece is going to vary more quickly. And so the basic idea is, if you can figure out how to find a good beam matrix, you can maybe use that over 1 minute. And then in the meantime, you continuously send pilots and training and estimate the combined channel and feedback that littler matrix there. And that's essentially the beam-based approach. And so you also, some of the other benefits you get is you do the compression, the feedback on these smaller effective channels. You also don't get overwhelmed by feedback. Now you still are, and you're taking advantage of the MIMO dimensions in that you're finding a good beamforming matrix, but of course not quite as good as if you knew the instantaneous channel. So that's the beam-based MIMO idea. And this is what was eventually adopted in 5G, a slight variation of it, which I'll explain here. The first phase is that base station sends signals on synchronization signal, we call it SSB, synchronization signal blocks. And nominally, you can think about them as being like broad beams. And they could be 4, 8, 64 such beams. The users report back which beam they prefer. And then in a second stage, the base station uses another set of beams, might be pointier, as illustrated up here, to then send training data to the users. The users estimate the effective channel, quantize it, send it back. Then, in the next stage, the base station does maybe the scheduling, multi-user MIMO calculations, and designs precoders to deliver data to the users. So this is the beam management stage that is adopted in 5G. And it's more or less like what I showed you, it's just that there's two steps of sending the beams there. Now, I went through this in some detail because myself working in MIMO a long time, I mean, I have found that most work in MIMO doesn't really embrace this beam management strategy despite it being in the standard for a good 5 years now. And it's not very well understood. Part of it because we need a 500-page bullet list of points to understand the standard in itself, and the ones on beam management are a good 50 pages probably at least. It's complicated. So this is actually what's going on, and I wanted to highlight a couple items here. So the standard explains that, okay, so there's these beams that need to be used for the SSB codebook to send that information on. There's another set of beams that come from what they call a CSIRS codebook for that second set of beams. There's a feedback quantization stage and then a data transmission phase. Now, the way that the final beams are constructed for data transmission, not standardized, of course, that's left up to the implementation. The feedback codebook, that has to be standardized because the user and the base station need to know the codebook where it's being quantized. But it turns out that those first two beam codebooks aren't standardized at all. Everybody thinks it's a wide and a narrow set of beams, they're DFT beams. That's what everybody thinks, but it's actually not specified. It's left up to the implementation. So the beauty of this is that one can take a data-driven approach to find those sets of beams. And this is something we've been working on recently in my group, and it's also been a topic of great interest in 3GPP. So the last few slides, I'll just highlight a little bit about what we're doing there. And where I see this as being interesting, so I also have a lot of skepticism about AI in wireless, in that we have a lot of models that are good. We have a lot of theory that's based on those models. There's a lot to be gleaned from that theory that is really important. So I don't want to throw it all away, but I do think there's places where we can have models that are parameterized, those parameters can be learned. For example, these two code books here. And these two code books can be learned based on a couple different sources of information. You could have just the past data, like which code books worked, which didn't work, right? That's past performance data. You could also have sensor data. Before I moved from UT Austin, which is a couple universities ago now, I'm not going to move again, I hope. I mean, I'm open to offers if you got something interesting. But no, I'm sorry, I'm not going to move. No, I'm not allowed to move again. I'm not allowed to discuss moving again, apparently. We were doing a lot of work with vehicular applications of wireless, and vehicles are awesome because they're big, they can have big antennas, they also have a lot of sensors. And so we were looking at different ways of using sensor data, camera, vision, LiDAR, radar, to help to parameterize the system. And it makes a lot of sense because if a camera can see that there's a building in front, the wireless millimeter wave signal is going to be impaired by that building, doesn't go, right? So there's a lot of things that can be learned. So these are both approaches we've been taking in my group over the year. What I'm going to mention here is just purely data-driven. I don't have too much time left, but I'll explain what we did. So this is my maybe my only PhD student to graduate from NC State, who just finished a month ago and is now joined the MITRE Corporation. His PhD was about designing these sets of code books. And so the first paper was to design the SSB code book. And SSB codebook design is kind of interesting because, so the premise is that about every 100 milliseconds, we can maybe use a new codebook at the base station. But the thing about SSB is that you want the codebook to also serve the users who aren't in the network because they got to get on the network, right? So we can't have that two users feedback and then I say, oh, okay, I'm going to send subsequently SSBs to those two users because then everybody else gets kind of screwed. So the data set is interesting because when we do the training offline, we also account for users that aren't in the network and try to design a set of beams that will serve both the existing users better and still support the new users that need to come in. And this is all done based exactly on the data that's coming in the standard, and we do everything to fit within the time constraints of the standard. So the inference has to be done in the standard. It's done offline, so the inference calculation, though, has to be done, of course, within that 100 milliseconds or less. The CSIRS codebook has to be designed much faster. That's even more challenging. So there's a lot of like really subtle, tricky parts here. I've worked on codebooks a long time. One of them is that even just this idea of the ordering. I mean, if the users are sending back, okay, I preferred code word 3, but a few time intervals later where the codebook is different, code word 3 is totally doesn't mean anything, right? So the ordering, the mapping to code words is complicated. And so what we did is something that makes a lot of sense from the way that MIMO channels are modeled, which is using this virtual channel representation, decomposing the channel into the contributions in different angular directions. Essentially, we can take a code word and map it into its constituent beam space representation. And so we produce an image from a code word, and then each code word in the code book has an image. So if we're trying to design 8 SSB code words, each of those code words will be mapped into 8 images. And then the problem to be solved is to take the 8 images from the current SSB, the feedback from the users, and then to design a new SSB codebook. So the neural network produces the new codebook from the inputs from the previous codebook and the previous power measurements. And then the network is trained using also the feedback from the users that we're trying to get on the network that weren't there in the first place. But when we operate the trained network, we don't, of course, have the new users because they're coming in. We don't know that they're there ahead of time. And our baseline of comparison is we try to see, okay, can we just beat the DFT codebook with this sort of a strategy? And naturally, it turns out that to be the case. There's a lot of details in how the convolutional network is created. My student is very good at coding. I'm sure did an excellent job here. And if you ask me any question, I won't be able to answer the details of it. Usually there's someone that says, oh, but what in like layer 3, what did you do over there? And I have to refer you to the paper there. So I won't discuss too much on the data, but you know, the net of it is that we were able to get roughly a 3 dB gain, 3.5 dB gain over the baseline DFT codebook. I've got between the 3 papers, there's probably 30 different plots to go through. I'm just going to show this one set here. So 3 to 4 dB, and it makes a lot of sense because, you know, like a DFT codebook, say in this room here, I mean, there's places where nobody's sitting, right? So why would we ever even throw energy there? So it does make sense that one can improve over that codebook. And this strategy has a lot of other advantages. Like if you take your network from one base station and put it into another base station, even with a different cell dimension, array size, it turns out it works well because you get a little bit more or less granularity in those beam space representations, those images that are created. So it actually scales well from like 32 to 16 or 64 antennas. Even if you train it on 32, we can fine tune it with just 60 seconds of data from one cell to another and get almost the same performance as if we trained the network entirely there. So it was an interesting result, and I think this several dB of gain is really non-trivial. And that's only from designing that first codebook. I still used the DFT codebook for the second stage. In the second work of the student, we actually also adapted the CSIRS codebook, but we had to design both SSB and CSIRS at the same time because the CSIRS one has to be designed in a millisecond. We couldn't do the inference fast enough. So the performance was even better there. And then finally, one of the big challenges is that all the initial simulations where we got that impressive 3.5 dB gain wasn't really cellular because there weren't any interferers. If you throw the interferers in there, performance gets worse because of the interference of the cell edge. But then if you do just a small amount of coordination of the code books between the base stations, you can recover all of that. And we've been using this NVIDIA Siona tool that can do almost real-time ray tracing to do the simulation. So that's been very exciting. And then finally, the most recent work, we've been incorporating sensor data as well, the vehicular occupancy grid, to try to show that if you know something about the dynamic nature of the environment, it can be even better. We've just submitted these results, and I don't have an impressive plot to show there, but it was another dB of gain over not having the sensor data. So with that, I'll wrap up. So as I alluded to earlier, I'm kind of stuck in MIMO at this point, and I just wanted to share with you where I see things going in the next phase. So what I'm actually really excited about right now is taking that hybrid architecture a step further and adding a reconfigurable antenna component. So not only can we adjust the phase shifters and attenuators, but even the fundamentals of the antenna itself. For example, leaky wave antenna, a parasitic array, and combining that with MIMO, and I see machine learning as a great application for this because it's very hard to derive the models to do all the configuration analytically. I mean, it's possible, just, you have to run some computational solvers. You end up with a lot of equations that are parameterized by a solver, so we might as well just use a data-driven approach directly. So that's it. Take any questions. There's time. All right, that's good. I think the coffee break is next, right?
The coffee break is coming
now.
Yes, we have 25 minutes, I think.
Yeah, the picture.
Awesome.
The picture.
Ah, the picture. Okay, yeah. Show it on here.
I guess that's the one.
Yeah, that's the one. Yeah. So much hair back then. I love it, man. This is the main reason I need this picture here. Yeah, this was after I saw Pulp Fiction, so I had these really nice John Travolta style sideburns and the hair.
In the background, you have Eric as well.
Yeah. So we've got Eric, Steve Halford. Yeah, Jihan is there. Yeah. I can't tell who's on the other side.
Yep.
Yeah. This was for the inaugural web page. What was this thing called, the web? Oh, we should make a page. Nice, thank you.
Thank you.